Jennifer JENIH, ANAK ENGKAMAT. I'm from J4 EM1104A. So today I'm conducting an experiment, which is experiment F4, energy losses in pipe and fittings. So the objectives of these experiments are to determine the losses in the pipe fittings related to flow rate and to determine the loss coefficients related to velocity head K. Before I forgot, flow rate is Q, coefficient related to velocity head is K, and one more objective is to compare the losses of energy or head losses, which is H, in different configuration of pipes. Okay, so before conducting any experiments, we should follow the safety procedures. So the safety procedures for this experiment are you have to use lab goggles, lab coat, and gloves throughout the experiment. And to make sure the bench valve is fully closed and the discharge valve is open prior to the experiment. Do not open the bench valve too fast. Okay, so the apparatus, okay, the apparatus, the energy losses in pipe and fittings apparatus has been designed for students to investigation of energy losses in pipe bands and fittings as well as gate valve. The equipment is mounted on a freestanding framework supporting the test pipe work and instrumentations. These pipe fittings include a meter bend, 90 degrees elbow, sweep bend, contraction, and enlargement. Okay, so the first is for the 45-degree elbow, and then the contraction. Actually, the contraction has the one for sudden contraction. Okay, as the streamlines, actually the fluid flows through sudden contraction looks like this. Okay, so as the streamlines approach the contraction, they assume a curved path and the total stream continues to neck down for some distance beyond the contraction. This section where the minimum flow area occurs is called the vena contracta. Beyond the vena contracta, the flow stream must decelerate and expand again to fill the pipe. The turbulence caused by the contraction and the subsequent expansion generates energy loss, which we have to calculate later. Next apparatus we have enlargement. Okay, for enlargement, it is for sudden enlargement, where the fluid flows through sudden enlargement is illustrated like this. So, as a fluid flows from a smaller pipe into a larger pipe through a sudden enlargement, its velocity abruptly decreases, causing turbulence that generates an energy loss. Assuming that the piezometer pressure on the face of the enlargement to be equal to that in the emerging jet and the momentum flux is conserved, the total head loss is calculated then, the same as sudden contraction. Okay, so next we have 90 degrees elbow water inlet connection. This is where the water enters. 90 degrees short bend, manometers bend, where it is used to measure the head loss. And then we have gate valve. It is to allow or disallow the water entering differential pressure gauge. And then we have 90 degrees elbow, the second elbow, the second 90 degrees elbow, and water drain connection, which is used to drain the water. It is used at the end of this experiment. Okay, so we're moving on to the procedures of this experiment. Okay, number one, the first thing we should do is place the apparatus on bench, connect inlet pipe to bench supply and outlet pipe into volumetric tank. Secondly, with the bench valve fully closed and the discharge valve fully opened, we have to start up the pump supply from hydraulic bench. And then we need to slowly open the bench valve until it is fully opened, which I have mentioned just now, not to open it for too fast. Okay, and then when the flow in the pipe is steady and there is no trapped bubble, start to close the bench valve to reduce the flow to the maximum measurable flow rate. By using the bleed valve, adjust water level in the manometer board. We have to note that we have to retain maximum readings on manometers with the maximum measurable flow rate. Okay, so take note here, a lower flow rate will reduce the water level while higher flow rate will increase the water level. Okay, next thing is note readings on manometers and measure the flow rate with the volumetric tank. Means that the readings on manometer and the measure in the flow rate, we have to jot them down in our lab sheet. Repeat the experiment with different flow rates. The flow rates can be adjusted by utilizing the bench flow control valve. And the last one is to plot graph differential piezometer head against the velocity head for each device and will determine the loss coefficients. So I will show the data that I have jotted down, and I have the data that I have achieved in my next video, and I will show my tables, my data tabulation, and the graphs that I have plotted. So this is the video of me calculating the volume flow rate, where I get to change the unit because
So
the volume
this
given
is a
is
video
in
of
liter, so
me
I change it to meter
calculating
cube,
the
where 4 liter equals to
first
0.04,
one is flow rate
0.004
where
meter
I
cube,
use
and the formula for volume flow rate is that Q equals to V over T. So the next one, I calculated the small v, VQ over pi d square, which I'm currently calculating right now. This is all for all values in the table. And next one, the one that I'm calculating right now, is velocity head, where the formula is v square over 2g. V square is taken from the small v I've calculated just now, and 2g is 2 times gravitational acceleration, which is 9.81. Next one, I'm calculating the difference in piezometer head. For data 90 degrees elbow, the formula to calculate is H1 minus H2, where I get to change the unit in the table, because the unit in table is millimeters, so I change to meters. I did it for 45 degrees elbow, short bend, sudden enlargement, sudden contraction, and 90 degrees elbow number 2.
Okay, so this is the video of me tabulating my data. This is for flow rate. Q equals to V over T. Just writing down all the values that I have calculated just now. And this one is for table 3 according to the lab sheet. So just take all Q, calculate V, small v, velocity, head, and 90 degrees elbow, H1 minus H2, 45 degrees elbow, H3 minus H4, sudden enlargement, H5 minus H6, sudden contraction, H7 minus H8, short bend, H9 minus H10, and 90 degrees elbow number 2, H11 minus H12. So I'm just writing down all the things that I have calculated. So this is the table I'm doing for graph, because after this I'm going to transfer all the data to a graph. This one takes a bit too long because I was facing a little bit difficulties. I don't know what happened to my laptop, but I'm able to fix it. The line on the graph just can't come just can't appear, and this time I managed to fix it. Okay, what I'm trying to say here is that when I reverse the graph, because the y-axis is normally on the left side, but it is not tally to the x-axis, where the x-axis seems descending. So I reverse the y-axis to the right side so that the x-axis will ascend just like how we normally do our graph. So the graphs, all of the graphs here, 6 graphs that I have done, all of them were directly proportional to the x-axis. So it means a differential piezometer head is directly proportional to velocity head. So I've changed to reverse graph, naming all the title.
Okay, in conclusion, all three objectives I have mentioned just now are achieved, where I am able to determine the losses in the pipe fittings related to flow rate. I got the flow rate already, and I'm able to determine the loss coefficients related to velocity head, and I'm able to compare the losses of energy head losses in different configuration of pipes, where the configuration of pipes um, were divided into 6. the 90 degrees elbow, 45 degrees elbow, sudden contraction, sudden enlargement, for short bend, and 90 degrees elbow number 2. Okay, and from the graph that I have plotted just now, it is true in the theory where it stated the head losses is also proportional to the velocity head of the fluid. So based on the graph that I plotted just now, I can prove that the head loss is directly proportional to the head, to the velocity head. So the application of energy losses in pipe and fittings is that it is used in the transportation of fluids, for example, water, petroleum, gas, and etc. So the error for for this experiment that may have been done by the person who is conducting this experiment is that the reading, okay, the conductor may not place their eyes perpendicularly to the reading scale, and the values may be slightly different because the person who conducts the experiment may be rounding off the values during the calculation, so it will give slight difference in this experiment. So that's all from me. Thank you for watching, and goodbye.